speaker from yesterday who is going to wake us up now after the coffee break. So Fischer, I think a lot of us already know who he is. So his group leader is Max Planck, also one of these guys who managed to have several different affiliations and do well at all of them. And he's going to tell us about interactions of cells with ultrasound and magnetics. Please.
Okay, yeah, thank you very much. So I apologize. Yesterday was three plane rebookings and cancellations, and there was thunderstorms. So at the end, the last one didn't make it, so that was it. But I'd like to maybe pick up on some of the themes of what I heard and talk about tools or mechanisms to allow for interactions with cells. So this is my research group and funding, and I'll try to mention people as I go along. Okay, so one way is observing biology, and the other way is maybe interacting with it. So to have probes, but maybe also ways of stimulating or triggering things. And if we have a meeting like this and there's a lot of microscopy and we want to stimulate cellular things, then I think one of the prime examples is probably optogenetics, which is extremely precise in triggering action and also observing. But it is, because it is an optical and an invasive technique, it's very directed, and there are still questions that one might want to answer in a similar way. Can you have a tool with which you can probe and measure and maybe at the same time stimulate? So that's a little bit the theme. And of course, this is based on some rather fundamental, interesting photophysics, which I'm sure will be a Nobel Prize at one point. We don't know yet when. And if you want to go deeper in the body, then optics will become problematic at some point. And so we can take inspiration from, let's say, reception in biology, magnetoreception. Animals somehow respond to magnetic fields, and the magnetic field can penetrate very deeply. And this is in itself an interesting topic. How does biology interact with, for instance, weak magnetic fields? There are obvious ways. We can use nanoparticles, we being bacterial cells, and exert basically a torque on the particle via the field, and it allows it in finding food and basically restricting itself. So this is maybe less debated. More debated are other mechanisms, one of which involves interesting idea that in the eye, during photoreception, you generate a radical pair mechanism which is sensitive to the magnetic field. This is one of the theories, which is rather fundamental because it involves quantum mechanics and magnetic detection. Whether it's true or not, people don't know because there are also other mechanisms, and this is quite a busy field because very late here, this is 28 now, this May. The next interesting theory is that maybe it's macrophages in the liver containing superparamagnetic inclusions that influence the interaction with magnetic fields. So clearly there are signs that something as weak as an Earth magnetic field has an ability to interact with biology. Which ones, or if any of these is correct, it is a different discussion. But taking this now, the question is, can we take things like, for instance, magnetic fields, or I will also talk about ultrasound, things that can go deep in the body, and can we use them to measure, probe, or stimulate? And because I heard several things related to electric fields, I actually changed my talk a little bit. I'll also talk about something on electric fields. So let me start, and this is a little bit the change I made due to discussions, tools to probe and interact with cells that are not connected to the outside world, so basically wireless probes. And one is going to be making nanostructures and using them to interact with biology. And the other one is going to be to use fields and use the interaction of, in this case, mechanical waves to interact with cells in biology. So this part of the work has actually a long history for me. It was at a time when I was at an institute where people studied by the locomotion of bacteria, and that inspired us to build something that could be used at this length scale so we can use it as a probe. That's, it goes back a long way, and one of the projects I did as an independent young group leader then trying to think about this flagellar locomotion, which is like a corkscrew propulsion, and can we build something mechanical, physical, that we can control so that we have something on the length scale of bacteria or smaller that we can use to probe and actuate. That was something we wanted to do because we were in an institute where these questions were being asked from a biology point of view. And this has started something we have done for many years now. We have built setups that can do this. I'll tell you how. And we use them as small local probes with which we can interact with magnetic fields. And I brought it back into this talk because we can also interact with electric fields. So how do we make these structures? If you go into the gas phase, you can heat something, you get a vapor plume, and you can make very nice thin films. That's what people use in a lot of technology, coatings. And so for this way of making these probes, we want not continuous films, but we want to have discrete nanostructures, and we want them all to be the same. So we actually changed something here. We are using a very oblique angle deposition. The first ones were not done by us. They go back quite some time. They were used for optical films. But usually they were quite large structure, micron structure to make optical films, and we worked hard in trying to get nanostructures out of this. So the idea is, can you use small nanoparticles as seeds, and then if you deposit on such a structure, because of the geometric shadowing effect, you can grow different structures in parallel, and if you control your substrate, for instance, you rotate it, you can actually grow shaped structures. And if you want to do this and you want to make very small ones, you need to make patterning with very small particles, and you need to prevent the diffusion of what you put on these structures. Otherwise, you just get blobs, okay? Because everything is heated, melted, has a lot of kinetic energy. And for this, we are actually using an extreme angle. We are using an angle of only something like 3 degrees of normal. So otherwise, you don't get this shadowing. And we use particles that are actually smaller than 10 nanometers. So we deposit typically on 5 nanometer particles. And the kinetic energy of these vapors is too high. You would just get blobs. So we actually need to cool this. So we use liquid nitrogen cooling to prevent this diffusion. So this is something we have worked on. And here are some examples of things we can make. Here are some helical structures. They are 90 nanometers tall, made out of plasmonic metals, and this is the whole wafer full of them. Or we can make different materials one after another with different kinds of shapes. And so this has been a workhorse. It's already more than 10 years that we did this. And you can actually combine materials, you can make sequential, you can make alloys, and so it's quite a powerful tool, at least in our lab. And so one of the things we did back at Harvard was to try and make these structures the same size as bacteria. So this is now made out of glass. You can see them. They're about 1 billion per square centimeter. They are functionalizable. They can be taken off the surface by just shaking the surface. And here is one fluorescently coated, observed in the microscope as we steer it with magnetic fields. Okay, so this is our nanoprobe that we can move around and that we can use now and functionalize it, and we don't need to attach it to the outside world. And since we had some discussions here and there, I want to show you a movie by, actually, he was the postdoc at the time, he's now a professor himself in India. This is taking one of these and we can put it inside a biological cell. This is the little particle, this is the cell, and you can start navigating inside and you observe, depending on its motion and behavior, some aspects which are to this rather complicated, inhomogeneous, non-linear rheology inside a medium like this. And by wobbling it and analyzing the dynamics, you can actually infer something about the local rheology. So it's like your 500 nanometer rheometer that you can have inside a cell. But this, I didn't want to get into. I actually put this in because I wanted to talk about another aspect, because there's a lot of sensing here and using electric fields. So I thought I'll switch something out and switch something in. And this is now to make a probe, which is a SIRS probe. I heard that word in a meeting a couple of times. That is not attached to anything and that you can steer around. So the idea is we start off with particles We grow them large enough so we have a substantial plasmon resonance. So this is by our growth method. We can go 10 nanometer, 20 nanometer, 30 nanometer, 40, whatever you like. You can choose this so that we are at the right wavelength. Then we grow a stem on this, which we do by an oxide. And at the very end, we put a tip on there, this little angle tip here. This allows in the experiment to tell up from down a little bit more easily. So this is a small little magnetic handle to allow it to be sure that we know it's standing upright. And then we can make lots of them and take them off the surface, and then we get a probe like this. This is 1 micron. So our SIRS probe is a 50 nanometer particle at the end of this stem. And the stem we use because of its dielectric properties, because we can steer and control it with electric fields. That's the idea. So these are things that are, it seems very familiar here in this institute also. You can make cells, you can make in-plane electrode pairs, and then you have top and bottom, so you have all directions available to electric fields. You can have a chamber in there, and you can fill it with liquid or whatever you want to look at, and your little nano probe, which is sitting here. I should say this is a long-standing collaboration with my colleague, Professor Pham at UT Austin. And so, because you have now these electrode pairs, you can apply DC fields, you can apply oscillating fields, and we can go up to megahertz. And very interesting dynamics happens because depending on how fast you go with the electric field, you might be polarizing, or the ions may follow or may not follow. So this gives rise to some interesting behavior. And so you can torque it, you can just rotate something in an electric field because it wants to align due to electric function. You can give it basically rotation, either because there is an in-phase component, that's the polarizability, or an out-of-phase component, which would be the imaginary part. All of them play a role. You can apply all of them, you can watch what you're doing, and then you apply the electric fields to see whether you can control this. And so the name of the game first was, if you take a nanoprobe like this in water at room temperature, how precise can you actually keep it? Because with electric fields and Ehrenfeld's theorem, we cannot find a stable trap. All we can do is we can keep it moving in the right position. So unlike some other things where you have a stable trap, an optical thing is a stable trap. Here all you can do is you can keep pushing and rotating it to prevent Brownian motion. So the first exercise was with Hyuna Kwon, she's now a professor in Korea, to take one of these. This is the dot, is the center of the particle, the center of our wire, to show whether we can control this well. And these were ladies I was collaborating with, so they decided they were going to draw a ballerina, and every orientation, every rotation, every tilt angle is full control. This is not on the surface, this is in fluid, away from the interface, at room temperature in water. And you can see we have 63 nanometer positional control and about 1.8 degrees angle control of 1 nanowire in solution. So we can basically make this thing dance according to the electric fields. At any moment, the DC and AC fields are constantly being updated to get this kind of motion, okay? And so here is the ballerina from Emma Pham and Hyuna Kwon that they were able to show inside the solution. And so it shows, even though it's not a stable trap, and even though we're at room temperature and we are fighting Brownian motion, you can, with electric fields, get really, really excellent control. And so this is, of course, nice, but it's not useful. So let's do something useful. And here are, by the way, the various angles, whether you tilt it out of plane or in plane or whatever, requires the combination of these field components. And so what could we possibly do useful with this? And for this, I showed you the structure. So we have now a wire that we don't need to attach. And at the end of the wire, we put this nanoparticle, which in our case is a 50 nanometer gold particle, which we could then illuminate from, for instance, in a microscope from below. And then we locally excite a plasmon resonance on this gold particle, which we can use to detect the light. We don't see this, we don't see the rest spectroscopically, because we're just looking for the plasmon signal. And so the idea was, can we take such a wire and control it in solution and bring it to a bacterial cell so that maybe the tip of this probe can be used to measure the metabolites that are released by the bacterial cell into the fluid solution. And so can we steer it to the bacterial cell? Can we take a spectrum and can we record the spectrum? And then as we move away from this thing, of course, we should see some decay in the signal. And this is what we did. So this is the experiment. This is a piece of dirt. This is very useful because then we know what we're doing. This happens to be the probe, and this happens to be the bacterial cell. The probe is standing vertically up, and what we can do now is we can either move the probe to the bacterial cell or the bacterial cell to the probe. So this is the E. coli. So you can change the position of these, and you can, in this particular case, bring them in sync while you're trapping your probe. And then you can bring the probe in contact with the bacterial cell, and you can record a plasmon cell spectrum from the metabolite in water that is released by the bacterial cell. And then you can, of course, also increase the distance. And as you're increasing the distance, you can take spectra consecutively as you're moving away. So we can try and see how much of this metabolite has diffused in the solution. So this I put in because there were various discussions about control of a source type spectra, but it goes in the spirit of controlling a structure in a wireless way, in this particular case, to do some measurement. I now want to switch gears and want to ask if we can also use fields to stimulate something. And another component in these lectures that I heard so far was actually holography. So I will bring you yet another form of holography, but it has nothing to do with light. It has something to do with ultrasound. So we are familiar with sound waves. Sound waves are mechanical waves. We can generate them by oscillating a piston, and then we're compressing a medium, and the compression and decompression will travel through the medium. That's what we know as a sound wave. And if we're above 20 kilohertz, we call it ultrasound. And so what do people do? They, of course, use this, and most of you have come across this in a medical context. There might be a scanner like this that emits typically very boring waves. They're either plane waves, they're either focused, or they are diverging, but they're nothing special. One just uses them. And the magic, however, when you do ultrasound imaging in medicine is that you record the echo signal, and then you do your inverse calculation to figure out what caused this in terms of reflection, scattering, etc. But the projection is really very trivial. In fact, I liken it to this. I think the ultrasound field in terms of projection is a little bit like what we would call either you take a torch and you just shine light in the room, or at best you take a lens and you burn something, which is, by the way, an approved medical procedure, which is very, very successful, by the way, for focused ultrasound therapy, where you can treat things like essential tremor without drilling any holes in your skull. You focus the ultrasound into the right region, and by destroying a small area of tissue, you can interact with the brain in that way to treat something. But this is quite violent because all you're doing is you're destroying something, and maybe in many biological settings we want to have a bit more control and don't just destroy something. And this is the theme now, and I want to first tell you why it's actually difficult to do the projection of a complicated object. So here it's just, you take the transducer, the wave comes in, it's basically a lens, and then it focuses, which, by the way, is actually quite complicated because the human skull is a very uneven object. So that's a little bit like sending light through a terrible glass, which will deform this. So they have this problem. And so if we could do better here, if we could project something very nice, like light, the light projector is forming these amazing images. Can we project something much more amazing than just focusing? That's my question. And I want to tell you why this is difficult. And then I want to discuss why it could be interesting in biology or medicine. Let's imagine you want to project this. It's a bicycle, right? An image of a bicycle. It's not difficult with light. If I want to project this with sound, I have to make sound waves somehow interfere in such a way to generate an image that I only have intensity where I see the lines, and I have other areas where the waves cancel out, right? But this is tricky because now we have a technical problem. Here is basically it's an artist picture, but it's based on a transducer with 90 elements. This is in air. The details don't matter. But you take 90 generating transducers, and in medicine people go up to 100 or so, and you basically fill half of the room with electronics to do it. If you take 90 and you want to set the wave phase and amplitude, then you can potentially make an image. But 90 is just far too few. This is the calculation of what would be the best signal, the best phase and amplitude at each point to get this, and this would be the result, which does not look like a bicycle. And the story is actually quite simple. If you're a physicist or not a physicist, it's a little bit like painting a picture. If you paint a picture with 90 pixels, it's not going to look very great, right? How can we do better? And this is now the acoustic hologram. So in light, it's very well known, but strangely enough, for whatever reason, people have not bothered with this in acoustics. And this was something that my PhD student Kai Melde was able to do. So can we fix this problem and get the ability to form ultrasound waves and thereby mechanical waves with which we can exert forces and do this much, much more precisely than just shining light like that. So he chose the peace dove, which I think is a very good symbol nowadays, right? Can we project the peace dove with ultrasound? So at the end of the day, the idea is if you go in your solution, in your tissue, anywhere, and you can do pressure measurements, can we see, wherever we see a line, can we see high pressure, and where we see no line, we see no pressure. And this is where the hologram comes in. I will not get into the details, but we can compute what this should be in terms of what the input wave should look like. And this is here the image that we can compute of the input wave. This information tells us if you are able, it's now calculating this for a circular transducer, if you are able at each point to give one of these phase values between minus pi and pi, you should get this, okay? So we can calculate what we should do. Now we need to find a way to shape our wave so that it accumulates this correct phase so that it can diffract into this object or this image. And the solution is actually really, really simple. Because ultrasound wavelengths are just the right kind of wavelength, you can go to your boring 3D printer down the corridor and take this computed phase map and translate it into a height map. And as the wave is propagating through the medium, if it propagates through more medium, it accumulates a different phase than if it accumulates through little medium. So by the height, you can set the phase, and with this alone, you basically, with this $1, €1 thing, you have the equivalent of 15,000 ultrasound transducers. And so this is what Kai did. He computed this, he made this, and then he stuck it onto a transducer, and then you can go into a water tank and you take a measurement device and you measure what is my pressure, and this is what he got. So this is now the projected pressure pattern. This scale is 0 to 50 kilopascals, it's a pressure, and this is the pressure in water. It's not an image, it's pressure, okay? And we all know that pressure differences give rise to forces, so we should be able to exert forces now, and we can project how we want them. And this is what we did next. This is a suspension of particles. You switch on the sound, you can make these particles rise to the top of the beaker, or you can let them disappear again, okay? You have the ability now to control forces, and you can do this based on your design, which is your calculation for your hologram. And so I want to now tell you something very quickly, and then I want to come back to more cellular things, because I'm actually myself quite amazed by this. This is a collaboration where we want to use this now, and this part is, from a biological point of view, less surprising. We want to use it to control the neuronal processes, basically what the mouse thinks or feels with ultrasound, okay? And the experiment we're doing is a collaboration with my colleague Jan Siemens at the University of Heidelberg, and it was postdoc Tanasi who did this. So what are they interested in? They are interested in how a mouse senses temperature. And it does it by the blood coming up near that region of the brain. It detects whether there are temperature differences. If there are temperature differences, it will decide, listen, it's too hot, you should cool down, or something like this, okay? But the traditional neurobiology required to insert a metal wire, a heating wire, into the brain, into this region, to put a current and to heat that brain region, right? So great opportunity for ultrasound, especially if you can control the focus very precisely. And so this is what we did. Tanasi built a helmet. The helmet is focusing to 500 microns in the hypothalamus, which is the region which is sensitive to brain. There are no holes drilled. All we need to do is we need to cement the helmet on top. And this is the mouse, and the mouse is in an infrared image, so we can watch its temperature. And by firing here, you can increase the temperature by 1 to 2 degrees in this 500 micron region. And by increasing the temperature to 1 to 2 degrees, you can get the mouse to think my whole body is overheating, okay? But it is never overheating because it's always very cool and comfortable. So you are just triggering this neuronal process by stimulating with ultrasound. So the mouse runs around. You can see it has a tissue region, which is called the brown adipose region. It pumps blood into here. It pumps blood into this, and then it will lie down and it will think, my God, I'm overheating. It's like summer, I should sleep. The clock runs for half an hour. The mouse is always cold. It's green and blue. It sleeps basically for 30 minutes after this one ultrasound trigger. And then after 30, 40 minutes, it wakes up again and it decides it must be good. It goes off and drinks something, and then it runs around in the cage. So you can basically trigger this biology with a very short minute ultrasound pulse, and the mouse will think it has overheated. Okay. This is something that is based on temperature. One cellular control, which you can also do by this mechanism, which is probably interesting to some of you, is something I would like to bring up, which is a work by a colleague of mine. This is Peter Wang at University of California, Southern California. And what you can do is you can basically take this ultrasound. I should concentrate on this one. You can take the ultrasound and you can take a cellular region, and for a very short moment, only a few minutes, you get this up to the high 30s, and then you can, for instance, trigger the expression of heat shock protein. So basically, if you wire a genetic circuit in which you have heat shock protein, you can take a region in the body and you can stimulate a genetic circuit only in this region, because only in this region you have put the ultrasound. Then you have triggered the genetic circuit, and this will then, for instance, induce things, for instance, in CAR T cells to activate them, etc., which is kind of a powerful technique. And I should come to close very soon. You can also use the forces to basically assemble biological materials like cells. People are very much interested in organoids, and they usually grow them in very tedious ways, and they come out, some are big and some are small. And this is actually a problem in a lot of the drug screening, because the variability in the organoids themselves are so high that it's very hard to have any reasonable screen. So can we use these forces and make very nice organoids or spheroids or assembloids that are very regular? And so the idea is we can go into a suspension. We don't have to do bioprinting. We can assemble these things with the sound. And it's actually an interesting physics, because you would never expect this to work, but it still works. And here is what you can do. This is in a suspension. A spheroid is assembled with ultrasound, which shouldn't happen. And here is Pac-Man in a petri dish, where you have the cells suspended in the container. And by applying this correct calculated ultrasound field, which gives you this image, you can see that we can assemble Pac-Man inside normal labware. We don't need anything special with this plastics. And here you can assemble cellular structures by this. One thing that's actually quite nice is that, unlike bioprinting, which people use in tissue engineering, which has a relatively low cell density, usually far below physiologically relevant. We are almost physiological density, so we're about 10 to 100 times more dense than bioprinting, and you don't need to print anything. All you need to do is you assemble your cells in suspension. So this is maybe an interesting thing. And with this, I think my time is up. I was going to talk about interaction with cells and ultrasound, but it's 30 minutes on the clock. And with this, I think I should end. So thank you for.
Thank you very much for an illuminating talk without much light and being on time. Questions, I'm sure, abound. None. I'll start. What kind of forces can you apply with the screws that you were showing from the beginning? You know,
they are typically in the depends on, of course, force, pressure, and size. It depends on tens of piconewtons. Is the head of the point? If the point is something like 300 nanometers.
And the electrorotation you were doing, does that only work under the right ionic conditions and so on?
No, because it's magnetic. So the screws are magnetic.
But the electrorotation you were doing.
The electrorotation, yeah. The electrorotation actually also works under higher ionic strengths because we typically work at higher fields. So at very high frequencies, the ions often don't manage to respond. But it's correct, they have an influence, and you need to take that into account.
Are you going to match the classes Mosotti factors?
No.
Yes. I am continuing on that, on the forces. Okay, so 10 piconewtons you said is, so for which size of the particle?
This is in the case of the magnetic. In the electric, it can be stronger. In the case of the magnetic, it's something like a few piconewtons. When the important part is what is the cross section you press through the fluid.
Right,
that's about the diameter of 300 nanometers.
Okay, no, I was just aiming to see if you can actually break some of the non-covalent bonds by going through 30 matrices.
No. So with magnetics, it's very, very hard. With magnetics, it's very hard. With the electrics, you can get to the famous nanonewton levels, but your structure needs to be bigger.
I didn't want to go to nanonewtons. I wanted rather to stay below nanonewtons, so something which is non-covalent interaction, like to go through the matrices or something. Because you said it goes through the cell, right?
It is inside the cell, but we don't penetrate the membrane. So we cannot.
No, I know that.
But it is able to do this, and we have examples. We're able to go to the mucus in the stomach. We're able to go through the vitreous of the eye. So we're able to do this. But usually, you also need to worry about your surface chemistry. You need to actually worry about adhesion and other things. So just mechanical force often not enough. But if you don't have adhesion, it's possible.
Okay, that's interesting.
Another question there?
Yeah. So do the spheroids or cell aggregates maintain a stable shape after you turn off the ultrasound wave?
No, if you just assemble in suspension and you turn off, things will fall apart. So typically the way we go about this is that we have a matrix which we can gelate. So we assemble and then we just fix it the matrix in which it is. So this is either by temperature and time or photo cross-linking.
May I just continue? Then?
No.
Sorry.
Super presentation and enlightening, as you mentioned, without using light. My question concerns a little bit on that dimension that you can control. So one idea is how sharp are the corners?
In which method? The ultrasound?
The ultrasound.
Yes.
Yes, and the other question is how sensitive it is on the level of your Fresnel lenses, for instance.
Okay, so the resolution is first of all fundamentally given by the wavelength. And so if we operate at something like 5 megahertz, then we are around 300 microns. But if you assemble material and you present it not too much material, then only the material that is in the area can be assembled. And if you present it too little material, if you like, you can get finer than this. So in practice, we have achieved 100 micron cellular pattern or lines. You can get reasonably sharp edges. It is a little bit that we have to calculate a hologram, and this sometimes has constraints. You cannot put intensity arbitrarily somewhere. So we basically are sometimes constricted by this. So I would say the right angle is probably not possible. And the angle doesn't matter too much because it will find a plane in which everything is in focus, and it doesn't matter if that's tilted in the suspension. And we can actually also do this in 3D. So we have made the first connected three-dimensional hologram in solution, so you can actually form a three-dimensional object by assembly. And this is even possible in something like an epi. So we don't need to have anything special. You can put an Eppendorf, and you can put the sound. We need to come from multiple directions, and inside the Eppendorf you can assemble this. And it doesn't matter if something is slightly tilted because it will find the focus region.
And last question. Do you think the Havana effect has something to do with what you can do?
I didn't hear you, sorry.
The Havana effect, you know, the
Smoking cigars?
the microwave.
Yeah. Cuba. They are implicated in using extremely high powerful ultrasound. And the idea is that this high frequency will generate lower frequency effects. That you can, with high frequency, generate lower frequency effect is a well-known thing, and it's a major problem in a lot of these experiments because in animals, you can switch on the auditory mechanism. Whether they have built this device and whether it was powerful enough, I don't know. But from a physics point of view, it's possible.
All right, with that scary note, I think we have to thank everyone.